Now we're going to discuss a very important property of the incircle. Suppose you have a triangle and its incircle, and I've drawn here the angle bisector of this angle. Of course, it passes through the incenter. And then I've drawn a perpendicular from this point to the angle bisector. And it turns out that this foot of the perpendicular lies on the line defined by these two tangent points of the incircle. Now we're going to prove this fact. The first thing we notice is that if we draw this segment here between the center of the circle and this tangent point, then this here is 90 degrees. We know that in order to prove that these 3 points lie on the same line, we need to show that this angle here is 180 degrees. But we know that this angle here is 180 degrees. And so this angle plus this angle is 180 degrees. Therefore, we only need to show that this angle here equals this angle here. Well, consider this quadrilateral. It is cyclic because we have a right angle here and a right angle here. And therefore, this angle equals this angle here. Suppose that this angle here is gamma. We know that this triangle is isosceles because this segment equals this segment because they're both tangent to the same circle. And therefore, this angle equals this angle. Now, using the fact that the sum of the angles in this triangle is 180 degrees, we get that this green angle is 90 minus gamma over 2. And now we need to show that this blue angle is also 90 minus gamma over 2. Well, notice that this line is an angle bisector of this angle because it's the line that connects the vertex of the triangle and the incenter. Now, if this angle is alpha and this angle is beta, then this is alpha over 2 and this is beta over 2. We know that alpha plus beta plus gamma is 180 because of the sum of the angles in this triangle. This angle here would be 180 minus alpha over 2 minus beta over 2 because of the sum of the angles in this triangle. And so this, the complementary angle, would just be alpha over 2 plus beta over 2. Now the question is, why does it equal 90 minus gamma over 2? Well, we know that alpha plus beta plus gamma is 180, and therefore alpha over 2 plus beta over 2 plus gamma over 2 equals 90 degrees. And so 90 minus gamma over 2 would equal exactly alpha over 2 plus beta over 2. If you're curious, this is a picture of what happens when we take the analogous statements of the one we just proved for all the different vertices. So we have a triangle and an incircle, and these blue dashed lines are the ones that connect two tangent points of the incircle. The red lines are the angle bisectors of each of the 3 angles of the triangle, and they all intersect at the incenter here. And then we draw perpendiculars from each vertex, for example from this one, to each of the 2 other angle bisectors that do not pass through this vertex. So the perpendicular from here to this angle bisector here, and from here to this angle bisector, perpendicular goes here. And then it turns out that the feet of these perpendiculars lie on one of these blue dashed lines. For example, this point lies on this line. So if we take the perpendicular from this point to the angle bisector with respect to this angle, then the resulting foot would lie on the blue line that's drawn with respect to the third vertex of the triangle, so on this blue line. Analogously, if we draw perpendiculars from this point to, for example, this angle bisector, then we would expect it to lie on the blue line that corresponds to this vertex here, which is this blue line. Now let's think about what the analogous statement would look like for the excircle instead of the incircle. So these are the 3 tangent points, and I've drawn the blue dashed line that connect each pair of 2 tangent points on the excircle. Then of course I'm drawing the 3 angle bisectors that connect the vertices of the triangle with the excenter. So this external bisector, and this internal bisector here. And I'm gonna see how the intersections between the red lines and the blue dashed lines give us right angles. Well, let's see what makes sense. This blue dashed line corresponds to this vertex of the triangle because this is the one from which these tangents are drawn, and then respectively the blue line. So I've taken this vertex, and then I've taken this vertex from which the external angle bisector is drawn. And this point should give me a right angle with respect to the third point in the triangle, which is this one. And here it is. This is a right angle. Now let's see why it's a right angle. Well, the proof is of course analogous to the one we did for the incircle, but let's see it nevertheless. First, let's draw this foot of the altitude to the red segment, and we're going to prove that this point, and this point lie on a straight line. And we're going to do this by proving that this angle here, so this angle but with respect to this point, equals this angle here. So again, this angle but with respect to this point. First of all, we know that this triangle is isosceles because this equals this. And so if this angle is alpha, then this angle is alpha divided by 2, and this angle is alpha divided by 2. And that's of course because this is 180 minus alpha, and the sum of the angles in this triangle is 180. Now we only need to show that this angle here with respect to this point is alpha over 2. First, let's notice that we have a right angle here because this is a tangent point to the circle. Then this quadrilateral here is cyclic because this is 90 degrees and this is 90 degrees, so their sum is 180. Then this angle, which we need to prove is alpha over 2, we can move it here. So we need to prove now that this angle here is alpha over 2. Now let's denote this angle by gamma and this angle by beta. So this is gamma over 2 and this is gamma over 2 because this is an angle bisector. Now since this is beta and this is an external bisector of the angle, then each of the two equal angles here and here would equal 90 minus beta over 2. But we know that alpha over 2 plus beta over 2 plus gamma over 2 is 90 degrees because alpha, beta, and gamma are angles in this triangle. And so 90 minus beta over 2 equals alpha over 2 plus gamma over 2. And now, since this angle is alpha over 2 plus gamma over 2, then this angle, the complementary one, is 180 minus alpha over 2 minus gamma over 2. And this angle is gamma over 2. So because of the sum of the angles in this triangle, we know that this angle is alpha over 2, as desired. On this picture, I've drawn all the analogous statements of the one we just proved. The optional problem is, suppose we have a triangle, and we take its incircle and one of its excircles, and they touch the side at this point and this point. And then we take this vertex, and then we drop perpendiculars to this line, which is the angle bisector here. Then these four red points lie on one circle. So this quadrilateral is cyclic. That's what we need to prove. And here's the solution. Okay, a perpendicular from a vertex to an angle bisector, such as this one, should ring a bell. This point should lie on one of the lines that connect two tangent points of the incircle. So this line, or this line. And from the picture, we can clearly see it must lie on this line here. Similarly, we see that this point should lie on this line here, defined by this tangent point and this tangent point. Now again, let's mark the angles of the initial triangle, denote them by alpha, beta, and gamma. So this is gamma over 2 and this is gamma over 2 here. Now because this is alpha and this triangle here is isosceles, then this angle here equals this angle equals alpha over 2. Similarly, since this angle is beta and this triangle here is isosceles, then this angle is 90 minus beta over 2. But as we know, 90 minus beta over 2 is actually alpha over 2 plus gamma over 2, because alpha plus beta plus gamma is 180, and so alpha over 2 plus beta over 2 plus gamma over 2 is 90. Now, take a look at this triangle. This angle is gamma over 2. This angle here is 180 minus alpha over 2 minus gamma over 2. And so this last angle must be alpha over 2. And now see what we've got here. This angle is alpha over 2. And so this angle here is also alpha over 2 because this is a straight line and this also is a straight line. And now in this quadrilateral, we have alpha over 2 here and alpha over 2 here. And they both point towards this side. And therefore, this quadrilateral is cyclic as desired. Interestingly, we can get even more out of this construction. From this vertex of the triangle, we drop a perpendicular to one of the angle bisectors. And so, this point must lie on this line here, defined by this point of tangency and this point of tangency. And what's more, from this point we dropped a perpendicular to this angle bisector, and so this point must lie on the line defined by this tangency point and this tangency point here. And now we can get even more facts about this quadrilateral that we just proved it's cyclic. For example, consider this triangle here. It's isosceles and one of its angles is alpha, and therefore this angle here must be 90 degrees minus alpha over 2. And therefore this angle here is also 90 degrees minus alpha over 2. Now from this triangle here, we know that this angle is alpha over 2 and this is 90 minus alpha over 2. And so this angle is 90 degrees. Similarly, we can show that this angle here is also 90 degrees. For example, by observing that this angle is 90 minus beta over 2 because of this triangle. And because of this triangle here, this angle is beta over 2 and this angle is beta over 2, so this angle must be 90. And therefore, this quadrilateral is not only cyclic, but this segment here is its diameter. And so the center of the circle is actually the midpoint of this side here. But remember that we know that this segment has length semiperimeter minus a, if the a is this side. And also, this length is the same thing. It is the semiperimeter minus this side. And so this equals this. And therefore, if this is the midpoint of this segment, then this is also the midpoint of the side. So in conclusion, this quadrilateral is not only cyclic, but this segment is its diameter, and the center of the circle coincides with the midpoint of this side of the triangle.